So far in this chapter, we've learned how to deal with inverse and joint variation. We've learned how to graph simple rational functions. We've learned how to graph general rational functions. And we've learned how to multiply and divide rational expressions. So now we're going to add and subtract rational expressions. So we've done multiply and divide. Now we're going to do add and subtract. And also within here, we're going to come up with a new idea, which is the idea of a complex fraction. And a complex fraction is a fraction that has another fraction in the numerator and or the denominator. So it might look something like this: ax plus b over cx plus d over ex plus f over gx, plus h. So a fraction that has fractions in either the numerator or the denominator is what we would call a complex fraction. Okay, so we'll work with how we deal with complex fractions as well. So a problem of this nature is something that we might want to work with. If I borrow P dollars to buy a car and I'm going to repay the loan over T years with an interest rate, then my monthly payment can be given by either formula below. And we're going to look at how we go ahead and simplify and make one formula the other through simplification. Okay, and this is a complex fraction. You see, so what I'm going to be doing is I'm going to be taking a complex fraction and turning it into a regular fraction. And that's what I would have to do. And then once we've gone ahead and gone through and done this work, then we're going to look at what our monthly payment might be. Okay, so if we want to add or subtract when we have like denominators, so the important, right, like denominators, normally we would say common denominators is really the phrase that normally gets used. So like and common are the same basic idea. So once I have common denominators or like denominators, then if I'm adding, I add the numerators. And you notice the denominator doesn't change. And if I subtract the numerators, and the denominator doesn't change. So here are a couple of examples of what that would look like. So I take the 3x plus 7, that becomes 3x plus 7, over 5x squared. The most important thing for you to remember, I think the thing that students get confused about is the denominator doesn't change. So in this process of adding and subtracting, the denominator always stays the same. What changes is the numerator once I have common denominators. So the first step in an addition or subtraction problem would be creating the common denominators. And once I've made the common denominator, I get to ignore it, and it just stays the same. So what that looks like in practice is I'm going to do the subtraction. Now remember, it would be very easy because of the way these are ordered to say this is 9 minus 2x over x plus 1. But this is not correct. Okay, we don't want to write it this way. Polynomials are written in descending powers of the variable. So this is negative 2x plus 9 over x plus 1. So it would be okay to do this for a step, but then I have to put things in the correct order, and it would look like that. Okay, 15 plus 5 is 20. Over 4x. We also want to make sure that we look at the concept that we want to simplify these things completely. 20 is 4 times 5, and I can cancel the common factor of 4 from the numerator and the denominator, and this becomes 5 over x. Okay, so once you've done the addition or subtraction, you still want to look at, is this fraction in simplest form? You should have already been doing that in fractions that had integer numerators and denominators. You still have to do that when they have polynomial numerators and denominators. So give that some practice. Go ahead and do problems 6 and 7, and then come back to the lecture. So when I'm adding or subtracting with unlike denominators, the first thing I need to do is I need to create common denominators. So normally that's done by taking a look at the different factors that make up the denominators, and then I create a new denominator that is going to have all of the individual factors of the other denominators, eliminating repetition. Now, there's a video to give you a sense of how to do that back in chapter 1. So if you take a look at that fraction operations video, that will help you do this. But one thing they haven't really showed you here is how this happens. Okay, so the important thing is I'm going to look at my two fractions. And what I do is, if I'm going to look at the factors that are in the denominator. Now, each of these has an individual factor, right? So my new denominator is going to have to be c times d. So with the first fraction, I'm going to multiply it by a fraction that will introduce the missing factor into the denominator. So I need to have c times d. This one has c, so I need to multiply it times d. If I multiply the denominator by d, I multiply the numerator by d, because this fraction here, this is really important, this fraction always has to equal 1. Okay, because I can't take an expression and multiply it by anything other than 1. Otherwise, I'm going to change its value. So over here, I'll have b over d. And here I have d in the denominator. I need c. So I multiply this one by c over c. And that's why this becomes a times d plus b times c. And that's how they got here. Okay, what they sort of didn't show you was that you're always taking to transform my fraction into an equivalent fraction with the correct denominator. I'm always multiplying it by another fraction that equals 1. Okay, and that's how it happens. Okay, and what that is we're creating the least common denominator. By evaluating all the different factors of the denominators and using each factor and eliminating repetition, that gives me the least common denominator. I can get common denominators just by using all the factors, but when I eliminate repetition, I get the least common denominator, which is going to be the most helpful for me. Okay, so let's go ahead and look at that in practice. So if we just want to find the least common multiple, the way that is done, now for me personally, the way that was taught in school was to take a number. Let's say I wanted to find the least common multiple of, let's say 2 and 5. And what you do is you take the bigger number, and you'd say, well, okay, does 2 go into that evenly? Well, 2 doesn't go into 5 evenly. So then multiply it by 2, and it's 10. Does 2 go into 10 evenly? Yes, it does. So this is the least common multiple. That's an algorithmic trial and error kind of method that works, but it really doesn't work very well for polynomials. What we're really doing is we're looking at the individual factors. The factor of 2 is 2, and the factor of 5 is 5. If I multiply them together, I get 10. I get to take the factors. So here I have factors of 3 and x, and here I have factors of 3 and x minus 2. So I'm going to use the 3. I need to use the x. Now, here's the 3, but I've already used it. I don't need to use this one. And x minus 2, that's a new factor. So this is going to be 3 times x minus 2. And I would prefer that you just make this 3x times x minus 2. This is what I prefer. I know that this is 3x squared minus 6x. I know that. But at the end of the day, if I'm doing an addition problem, which is why I would make the least common denominator, at the end of the day, I'm going to want to try to factor it and see if I can simplify it. So I might as well leave it in a factored form. Okay, so it's just going to save me work. And I would rather see your work in factored form so I understand that you knew what all the right factors were. Okay, so if I take these guys, I want to factor them. X squared minus 25, that's x plus 5 times x minus 5. And then I have x, and then I have x minus 5. So I'm going to use x minus 5, x plus 5. I'm going to use x minus 5. I'm going to use x. But when we get to this x minus 5, I've already used it once. I don't need to use that one. So it's going to be x plus 5 times x minus 5 times x. this will be my least common multiple. So it's this concept of eliminating repetition that helps you get the least common multiple. Now, to give you another example, what if I have x plus 5 times x plus 5 and x plus 5? Okay, now I'm going to use this x plus 5, and when you get here, you might think, oh, I don't need to use this because I've already used it. But if it repeats in the same denominator, then you need to use it however many times it occurs in any one denominator. I wouldn't need to use it a third time. Okay, so if it repeats within the same denominator, you have to use it the most number of times that it shows up in any one denominator. But when it turns up in a different denominator, then you get to ignore it as repetition. Okay, so go ahead and give that some practice. Find least common multiples. Do problems 11, 12, and 14, and then come on back. Okay, so now I want to go ahead and practice this. I want to add with unlike denominators. So I want to figure out what is my least common multiple. What will be my lowest common denominator? So this is 3 times x times x. Okay, so the x repeats here in the same denominator. I'm going to use all of those. And over here I have the 4. I have to use that, and an x, right? So I'm not going to use that x. And instead of putting an x underneath the x to say I'm not going to use it, I use this, I use this, I use this, I use this, and then I don't use that one. Okay, so this one doesn't get used. So my denominator will be 12x squared. Right? 4 times 3 times x times x. So what do I have to multiply 3x squared by to get 12x squared? Well, it's the item that was missing from the other side, 4. And if I multiply the denominator by 4, I multiply the numerator by 4. And over here, what do I need? I need the 3 and 1 extra x. I already have 1x, but I need 2 x's. So this is 5 over 4x times 3x over 3x. Remember again, these fractions that I'm multiplying by, they equal 1. They have the same numerator and denominator. That's the only reason I can do this. Okay, 4 times 8 is 32, and this is 12x squared. We knew that was going to happen. Minus 15x over 12x squared. So this will be negative 15x plus 32 over 12x squared. Now, I would still want to see, is there something I can factor? Like, for instance, if I could factor a 3 out of each of these, I could cancel it with the 3 that's part of the 12, but 32 doesn't have a factor of 3. So that's not going to work out. Okay, so sometimes once you've done the addition, or in this case subtraction, you end up with something that can be simplified. Okay, you always want to check for that. In this problem, it's a little more complicated. I want to factor this. Factors of 16 that add up to 8, that's 4 and 4. So this is x minus 4 times x minus 4. So I'm going to use the x minus 4. I'm sorry, I promised you I was going to use highlighters, so let's do that. I'm going to use the x minus 4 and the x minus 4. When I look at the other factor, it's x minus 4 again. I've already used it, so I'm not going to use that one. So this is the common denominator. So I don't have to change this fraction at all. I'll have negative 15x over x minus 4 times x minus 4 plus 12 over x minus 4, but I need 2 x minus 4s in my denominator, so I'm going to have to multiply it by x minus 4 over x minus 4. So this will become 12x minus 48. Right? And actually, I might as well just make one fraction at this point. I have common denominators. And here I have negative 15x. So negative 15x plus 12x is negative 3x minus 48 over x minus 4 times x minus 4. Now I could factor a -3 out of this, but it's not going to give me x minus 4 as a result, so there won't be anything else for me to simplify. I could leave it like this. If you want to see what that looks like, if I factor a -3 out of this, then I'll have just positive x here, and I'll have plus 16 over here. If this contributed to something that had a factor shared with the denominator, then I could simplify further. Okay, but this becomes my solution. I would accept either of these numerators. They're both correct. Okay, a couple more examples. Difference of two squares. This is x plus 2 times x minus 2. Sorry, x minus 2. So I'm going to use both of these, but I don't need to use that one. I already have. So again, this numerator stays the same. And I'm going to multiply this times x plus 2 over x plus 2. So this will be 15x plus 30. Now you notice I put parentheses around this. This is really important after subtraction. Otherwise you're likely to get the signs wrong. Okay, when I take the parentheses off, I'll have x plus 4 minus 15x minus 30 all over x plus 2 times x minus 2. And x minus 15x is negative 14x. And 4 minus 30 is minus 26. All over x plus 2 times x minus 2. Again, I could factor a -2 out of this. This could be -2 times 7x plus 13. But again, if it doesn't lead me to being able to simplify, that didn't really change anything. So both of these would be correct in my book. One last example here. Factors of 14 that have a difference of 5, that would be 7 and 2. So this is x plus 7 times x minus 2. This is, again, the common denominator. See, this x plus 7 is a repetition of what I've already used. So I'll have x squared minus 5. And again, this is all going to be over x plus 7 times x minus 2. And over here I have to multiply it by x minus 2 over x minus 2. So this will be minus, open parentheses, I'm going to have x squared. And I'll have minus 2x plus 3x, that's plus x. And plus 3 times negative 2 is minus 6. When I take the parentheses off, I'll have x squared minus 5 minus x squared minus x plus 6. So x squared minus x squared is nothing. I have a negative x minus x, and I have minus 5 plus 6, that's plus 1, over x plus 7 times x minus 2. Okay. You notice I didn't bother bringing this denominator down, because once I have the common denominator, it never really changes. So most of my work happens in the numerator. So I normally feel free to just go, well, there's no point in my transferring this down to this step and this step. As long as I remember to have it in my final answer, I could kind of skip it in some spots to save some space and to not get confused. Okay, so go ahead and practice that. Do problems 16 and problems 19, 20, and 21. When you finish that, come back to the lecture. So as I spoke about, a complex fraction is a fraction that contains a fraction in either its numerator or its denominator, and it could have both. So there are two different ways that you can do the work of simplifying a complex fraction. So method one involves taking the numerator and the denominator and simplifying them to be a simple fraction, and then divide the numerator by the denominator, which we've already learned. We learned in section 5.4 means I invert and I multiply. Okay, so what that is normally in a complex fraction you've got an addition or a subtraction problem in the numerator or the denominator. If you do the subtraction or the addition, it becomes a single fraction, and then once you have a fraction divided by a fraction, do division, which we've already learned. The other method is to identify the least common denominator of every fraction, and that's important, every fraction. So you might have multiple fractions in the numerator and the denominator. The least common denominator for every fraction. And then if you multiply the numerator and the denominator by that least common denominator, it will get rid of all of the fractions and leave you with a single fraction that you can simplify. So let's go ahead and look at these two different methods. It doesn't make any difference what method you choose, but I'm going to do the initial method. So you'll notice here I have an addition problem in the denominator. If I do this addition, then I'll have a fraction divided by a fraction, and I can just do division. Okay, so that's what I'm going to do. The first thing I need to do is I need to look at my denominators. I have x plus 1 and I have x. So x plus 1 times x, that's going to be the common denominator. So I'm going to make the common denominator of x plus 1 times x over x plus 6 over x times x plus 1 over x plus 1. Right? Now you'll notice I'm totally ignoring the numerator. It's going to come back in a minute. Okay, so over here I'll have 4x plus 6x plus 6 all over, and I really should be in the habit of putting that around in parentheses. X times x plus 1. 4x plus 6x equals 10x plus 6 over x times x plus 1. Okay, so if I take this guy and I duplicate it, which I just did, and I bring it down here, now I'm ready to put my numerator back on it. 16 over x minus 2. So now if we invert and multiply, that's going to be equal to 16 over x minus 2 times x over x plus 1 times 10x plus 6, which also could be 2 times 5x plus 3. So I factored it just to see if this would make life any better. It really didn't. Okay, so when I finish out doing this, I'm going to have 16x times x plus 1 over 2 times 5x plus 3 times x minus 2. Okay, now I could go ahead and multiply this all out and then see if it's going to factor back out. That really it's about the denominator. The numerator is all fully factored, right? I have 16 times x plus 1. But it might make sense to go ahead and multiply this all out. 5x times x is 5x squared. 5x times minus 2 is minus 10x plus 3x, that's minus 7x. And 3 times negative 2 is negative 6. And then we might look to see if this factors any other way. Right? So if it could possibly factor another way, I really don't think it's going to. This would be just the whole answer. So if that makes sense, sometimes you have a bunch of different things here, and when you multiply them all together, they'll factor back out into a different set of factors. If any of them was x plus 1, then I could have simplified. But at the end of the day, this is the simplest answer. Okay, if we take a look at the second method, what I want to start identifying is all the different factors. And what might help you a lot is just determining when you have a lot of common factors in these denominators, this might be a better method to go about it. For instance, this is 6 over x plus 2 times x minus 2. So if I use both of these, you'll see that's a repeat, that's a repeat, that's a repeat. This is the common denominator. So if I take this whole fraction and I multiply it times x plus 2 over x minus 2, when I go through and I multiply, what's going to happen? So let's take this whole thing, and I'm going to multiply it times x plus 2 times x minus 2. Again, I'm multiplying by a fraction that equals 0. And I also have to use the distributive property. So when I multiply these guys times the numerator, I multiply it times that fraction and also times that fraction. Okay, and when I multiply these two binomials times this fraction, the x minus 2's will cancel, and I'll get 3 times x plus 2. And when I multiply these times this fraction, both of these cancel with those, because that's what it is, and I just get minus 6. And that ends up in my numerator. When I take these and I multiply them times these fractions, when I multiply times 3 over x plus 2, the x plus 2's cancel, and I get 3 times x minus 2. And when I multiply times this fraction, 1 over x minus 2, the x minus 2's cancel, and I get 1 times x plus 2. And now what I want to do is I want to simplify. I'll get 3x plus 6 minus 6, which is going to continue to be just 3x. And in the denominator, I'll get 3x minus 6 plus x plus 2. So I'll 3x plus x is 4x. I'll minus 6 plus 2 is minus 4. If I were to look at this, this is 3x over 4 times x minus 1. No common factors to simplify. There I'm completely simplified. Okay, so depending on what you have, you would choose a method, one method or the other. They're both completely valid, and they both will work. What's important for you as a student to understand is by evaluating the problem at the beginning, picking which of these two methods is going to be the easiest for you to get through and involve the least steps of the least complexity. Okay, so that's what's going to lead to more quickly and more easily being able to drive to the correct answer. Okay, so go ahead and practice that. Do problems 31 and 34. That's an example of each method. And then come on back to the lecture. So we're going back to our first problem here. So if we go back to this problem that we talked about, we want to show that these two formulas are the same formula. Okay, and we want to do that by simply simplifying the first formula. If I do that, the first formula will end up becoming the second formula. Okay, so when we take a look at how this all goes about, right, I want to look at simplifying it. So I have p times I over 1 minus, if I simply apply the exponent, I'll have 1 to the 12t over 1 plus I to the 12t, and I used the property of exponents. Then when I have an item being divided by another item to a power, I can make it the numerator to that power divided by the denominator to that power. So that was the first step I did going from here to here. I applied the exponent. Now I want to get rid of this denominator here. So I'm going to multiply, right? I only have one fraction, that's great. So if I multiply by the least common denominator, that's 1 plus I to the 12t power. 1 plus I to the 12t power. This is still a fraction that equals 1. Then this is going to cancel out that. And 1 to the 12t power is just 1, right? And 1 to any power is 1. Okay, so when I multiply this times pi, I get pi times 1 plus I to the 12t power. And when I multiply this times 1, I get 1 plus I to the 12t power. And when I multiply it times this fraction, it cancels with the denominator and I just get minus 1. Okay, so now you see that this equals that, and I've done the first part of the problem. So I've shown that this formula and that formula are the same formula if I simply deal with the complex fraction and make it a simple fraction. And now they'd like me to find my monthly payment if I borrow $15,500 at a monthly interest rate of 0.5% and I repay over 4 years. So let's look at what these different things are. P is equal to 15,500. That's the principal. My rate is 0.05%, but that's 0.005. And my time is 4 years. If I plug all that in, so I said R, but they actually used I as the interest rate, so my mistake. So P times I is 15,500 times I, which is 0.005, times 1 plus 0.005 to the 12 times t being 4, 12 times 4 is 48. That's my numerator. And then over here I'm going to have 1 plus 0.005 to the 48 power minus 1. Okay, so now if I'm going to do this, I'm going to use a calculator most likely. So if I pull up my calculator, I'm going to want to do 15,500, 15500 times 0.005. 77.5. Okay, so that's going to be 77.5 times 1.05 to the 48th power. Right? So if I take 0.005 and I take it to the 48th power, that's going to equal this number. Well, let me write that down, 1.27 essentially. I'm going to go right back to my calculator though and do the multiplication because I don't want rounding error. So I'm going to get 98.463. Okay. So that's going to equal 98.463. So I've done my numerator. Okay, if we go back to the calculator, I'm going to divide this again. Well, basically it was 1.27, right? So, but let me go ahead and use, I don't want rounding error again, so 1.005 to the 48th power is that number. And then I'm going to subtract 1. Okay, so that's going to be basically 0.27. Okay, divided by 0.27. So if I go ahead and invert this, and I multiply it times 98.463, my value here is going to be 34.98. Yeah, basically 34.99 when you round, right? If I round up here, this becomes 5. 5 will round up to be 99. We're talking about dollars, so that's where we want to go. What did I say? 34? 34. 34.99. $34.99. Okay? So that's just working with these fractions, then simplifying the fraction, ending up with using the new formula to solve. And that's the end of this particular section 5.5.